I'm happy to be here again and to present, let's say, what the discussions are on European level, how the European seed sector, including, of course, the Romanian seed sector, is looking at new plant breeding techniques or new genomic techniques, as the Commission now calls them. The title of my talk, How Plant Breeding Innovation Can Help Sustainable Food Security. And I think sustainability is one of the main topics for the EU with the Farm to Fork, the biodiversity strategy. But with the current crisis, the Ukraine war and the climate crisis as well, food security is, of course, and productivity of agriculture is, of course, also highly important. And those new technologies can definitely help addressing those challenges. Just a few words on Euroseeds. So who are we? We are representing the European seed sector, seed and breeding sector. Members of Euroseeds are national seed associations, like the one in Romania, for example, but not only EU seed associations, but also seed associations, for example, from the UK, from Ukraine and Turkey. So more let's say, the geographical Europe and not limited to the European Union. And we also have direct company members, and we represent seed and breeding for agricultural crops and vegetables, while the ornamental breeding sector is more represented by the Dutch Seed Association, because most of those companies are based in the Netherlands. Some facts and figures. So our breeding companies each year put like 3,500 new plant varieties on the European market. So they are registered on the Common Catalogue of Varieties in the EU. And in total, we have currently more than 42,000 varieties available for farmers all over Europe. So which is a huge diversity and choice for farmers. Not all of those varieties are grown on big areas. Some, of course, are more successful than others. But in principle, farmers have a huge variety of choice. And one figure which is very important in the context of new breeding techniques or new genomic techniques is the R&D spending of breeding companies, which is up to 20% of their annual turnover. And with this, our industry is really highly innovative, and R&D plays a major role in developing new plant varieties. How do we look at those new breeding techniques? This slide shows, let's say, the evolution of new breeding techniques in plant breeding. Before Gregory Mendel, and we celebrate his 200th birthday this year, discovered the laws of genetic, breeding was more or less a one-tool activity. So breeders could just select from their fields the best plants and grow them in the next season. But after the discovery of laws of genetics, so we had many new breeding tools coming up over the past 150 years. From hybrid breeding over mutation breeding, tissue culture, etc. And the lines here should indicate that it's not about one tool replacing another tool, but it's adding to the toolbox of a breeder. And that's the same with the new breeding techniques, which I highlighted here under the term precision breeding, because they allow breeding to be more precise and more efficient. They also add to this toolbox. So it's not about replacing crossing and selection by those new tools, but using those tools to solve specific problems. And I think that's important also for a general understanding. We don't talk about using only those tools in the future. It's really about broadening the toolbox and helping breeders to address certain problems in a more targeted and more efficient way. What is the value of plant breeding? And we have a study here from 2021 on the socioeconomic benefits of plant breeding in specific countries, but also all over Europe. And the general outcome of this study was that plant breeding in the past contributed to 2/3 of the productivity growth on European agriculture, which shows that plant breeding is highly important in view of productive agriculture, and the rest, let's say the other third of productivity growth, goes back to, of course, the use of fertilizers, the use of chemical plant protection products, and the use of modern technologies in farming. But 2/3 of productivity growth goes back to genetic improvement of plants. In total, that's 1.16% of annual yield growth over all crops. So, of course, some crops are more and some are less, but in total 1.16%. So what would have happened if plant breeding had stopped 20 years ago? So we would, of course, have less yield today. And if we would like to compensate for that yield reduction due to lack of plant breeding, we would need to put additional land under production, so to keep up. And that would be the territory of Romania. So if we would have stopped plant breeding 20 years ago, we would need another 22 million hectares of agricultural land in Europe to compensate for that yield losses. And I think that's a very impressive figure also. And that's not new breeding techniques, it's conventional plant breeding. So now we are discussing the farm to fork and the biodiversity strategy. And I just put here on this slide the main objectives of those two strategies. And that's reducing pesticide use by minus 50%, reducing fertilizer use by 20%, also putting out productive farmland from production, so that's minus 10%, and putting more land under organic production, so up to 25%. And all this together, of course, has an impact on our agricultural productivity. So if we don't compensate for those, let's say, restrictions, which we will face under those strategies, we will face a productivity loss of around 23% in crop production. That's over all crops and over, let's say, the whole EU. But the study, which I just mentioned, calculates that also for different countries and for different crops, but the overall productivity loss would be around 23%. And how can we compensate for that? Well, plant breeding could help, of course, compensating. I mentioned 1.16% per year in productivity growth. But if you look at that slide, so if we would keep plant breeding at the current pace, we would not be able to compensate for those 23% production loss until 2030, when both of the strategies, farm to fork and biodiversity, are to be implemented. So only by 2040 we might be able to compensate for some of the crops, but that means we will be more dependent on imports and we will be less productive in Europe. And so the consequence is, if we want to use plant breeding to compensate for those productivity losses, we need to speed up in breeding, and the new breeding tools can help with this. So where can those new breeding tools play a role in the breeding cycle? And this slide just indicates how much time breeding takes. Of course, it's dependent on a crop, it's dependent also on where the starting point is, and this is why we say, well, these figures indicate up to so many years, but in principle, plant breeding for a cereal, for example, takes 10 to 12 years. For potatoes, it can easily take also 20 years. And the new tools can play a role in different parts of the breeding cycle. In basic research, of course, when you look at genes and you want to identify their function, you can use those tools to gain this information. You can also use them in translational research. So when you have some research on model crops, for example, you can translate these research into farm crops, and then you can use those tools as well. Of course, in applied research, for example, public-private partnerships between breeders and academia, to integrate those technologies in breeding, and this is specifically relevant also for small and medium-sized companies who don't have their own, let's say, molecular labs and facilities to integrate those tools. So they are dependent on public-private partnerships. And then, of course, when it comes to variety development, also here, if you have already nice germplasm and you want to integrate a specific new trait, then you can also use those technologies here. So in many different aspects, those technologies can help breeding, being more targeted and more fast, and helping to reduce the breeding time and to provide better varieties to farmers in a shorter time scale. So, as I said, those breeding tools can help speed up breeding, and we did a calculation here. So if we would just reduce breeding time by 18%, which would be for a cereal, for example, 2 years of breeding time, we could get an extra yield increase by 2040 of 2.6%, which is relevant because it would provide extra food for almost 20 million humans. It would avoid global greenhouse gas emissions by not putting additional agricultural land under production. And it would also preserve biodiversity because we can keep natural habitats for biodiversity, and we can restrict agricultural production to the land which we already have under production. So there are various contributions of those, let's say, time savings in breeding to the objectives of the EU Farm to Fork and Biodiversity strategy. Just one example here. It's an example on a fungi-resistant wheat, which is currently developed in a German private breeding project with many German breeding companies. And they want to, let's say, develop fungi-resistant wheat with those new breeding tools. And the study did some calculations on the economic effect, on the environmental effect as well. And if we would just grow this wheat on 10% of the acreage, on 25 or 50% of the acreage, and we could save 1 or 2 applications of fungicides, that could have a potential effect of reducing fungicide applications by 25 million applications. So this shows it could have a practical impact on farming when we would have those varieties available. How do our members, so Euroseeds members, look at those new breeding techniques? You know, there's a public discussion, it's only for big companies, the smaller ones don't have an interest, etc. So we wanted to find out. So we did a survey within our membership in 2020, and this is also published in a peer-reviewed journal. And we had 62 companies contributing to our survey, 53% of them small, 33% medium-sized, and 10% large companies, and that pretty much reflects also the structure of our industry. So we have many, many small and medium-sized companies. And all of them are more or less interested in this. Of course, the bigger companies have a higher interest. They have the facilities. They can easily implement those tools. But also you can see here the medium-sized companies, 86% would be interested to use those technologies. And also from the small companies, almost 50% would like to use the technology. But the European Court of Justice ruling from 2018, which judged that all those technologies need to be considered GMOs, had an impact already on the R&D activity and innovative capacity of our companies, because many companies stopped their research activities with those new tools. Some moved the product focus out of the EU. Some even moved their whole research programs out of the EU. So there is already a devastating effect on the innovative capacity of our industry just because of this ruling. And also we asked our companies, so what actually are the main concerns with the current GMO regulation that hinders you to invest in these technologies? And that's the regulatory costs, of course, because that's really, really high, up to 16 million just for an import approval, and we don't have any figures for cultivation approvals because there has only been one cultivation approval under the old GMO framework in 1998. Under the current GMO framework in the EU, we have no cultivation approval at all. And public acceptance is, of course, also a big concern. And then, of course, the legal certainty and the regulations and timelines for approval. So you probably know we have EFSA involved in the risk assessment. And even if EFSA supports the cultivation of a crop or the import approval, we still have the politicized process afterwards where the Commission and Member States decide on confirming the EFSA statement or rejecting the approval. And that's, of course, a big hurdle also and a big legal uncertainty for companies. How do other countries make NGTs work? What we can see around the world, and I will show a map on the next slide, many countries have established a case-by-case assessment of products on the basic principle: if the products are similar to conventional products, they are not regulated as GMOs. And those countries, and I have here the example of Argentina and Japan on the right-hand side, they have established kind of a decision tree mechanism where they ask from the developers of the product certain questions, and based on the information they get, they decide the product is a GMO or it's a non-GMO if it's similar to something that can also be achieved by conventional breeding. So there's no third category of products, it's either GM or it's a non-GM, a conventional plant. And it has a major effect also on those parties who develop those products. And this is also figures from Argentina. They already established their regulatory approach in 2015. And what you can see for those new NGT products, 66% of the developers were local developers, so either public developers or also small-sized companies, while for classical GMOs, it's 95% of foreign developers and also big companies. So enabling regulations have also the effect that the diversity of developers increases, and with this, of course, also the diversity of crops and products. And this is the map which reflects the current regulatory situation around the world. And many countries highlighted here in dark green are those which follow the similar approach as Argentina and Japan, for example, excluding those products which are similar to conventional products from their biotech framework. And still some countries are discussing their approaches, amongst them, of course, the European Union, that was mentioned already earlier. And only 2 countries are currently staying with their regulatory framework, that's South Africa and New Zealand. But also here you can see first African countries started to follow a similar approach as those countries here highlighted in dark green, specifically those in South America. And yeah, we think Europe should follow a similar approach. So that's our basic considerations for future policies here in Europe, and we think we should follow, as I mentioned, the approach. If a product is conventional-like, it should also be regulated as a conventional product, and Europe should follow more the countries which took a similar regulatory approach. And we have set up basic criteria for this. We say if there's no novel combination of genetic material, if the genetic material comes from species that could also cross with each other on a conventional basis, or if it's a result of a spontaneous or induced mutagenesis, those products should be regulated as conventional product because they are also indistinguishable from conventional products on a genetic basis. Conclusions. I think I could show you that plant breeding has a track record of contributing to sustainability already also in the past. It's all aspects of sustainability, the environmental sustainability, but also societal sustainability and economic sustainability for farmers specifically. These new technologies could provide additional opportunities for more sustainable farming by reducing the breeding time and by helping to have more targeted approaches by reducing also the complexity of breeding, specifically for crops which have a complex genome, which have, for example, long generation times. So specifically in those crops, those new technologies can help. Enabling regulations support local developments, as I've shown from the example of Argentina, and also increase the diversity of developers. NGT applications are versatile, can be used in many different ways for different crops. You can achieve GMO-like products, but also conventional-like products, and they should be regulated as such. And as I said, we should follow the increasing number of countries that have implemented the same principle in their regulations. And with this, I end my presentation and thank you for your attention and happy to discuss further.